Hello, today we will be covering 7.4 parallel lines and proportional parts. We're only going to do the first half of the lesson in this video. So your learning target is I can use proportional parts within triangles and parallel lines. When a triangle contains a line that is parallel to one of its sides, the two triangles formed can be proved similar using the angle-angle similarity postulate. Since the triangles are similar, their sides are proportional. So we have the triangle proportionality theorem. If a line is parallel to one side of a triangle and intersects the other two sides, then it divides the sides into segments of proportional lengths. So we have these two sides parallel here. They're marked with little triangles. This is dividing the segments into proportional lengths. So we are going to set up a proportion. That is something that we cross multiply to solve. And I'm going to highlight our pieces here. So we have AB over BC equals AE over ED. So you'll notice the proportion is set up where the two parts of the side are in one fraction for each of these. Okay, so let's do some examples. We have example 1, find the length of a side. So we are missing SU over here. It tells us that we have two parallel segments, RT and VU. It tells us that SV is 3. VR is 8, UT is 12. We're finding SU. All of that's already marked there. If we look back up at our theorem, we have the segments on the same side, the partial segments in one fraction. So I'm going to do 3 over 8. And because I have 3 over 8, I'm going to do x over 12. And then I am going to cross multiply to solve. And notice most of the problems in this chapter, we're doing a lot of cross multiplying. So then, once we solve, gotta pull up my calculator. 36 divided by 8 is 4.5. Go ahead and pause me. Try that you try. Okay. So, same idea for this problem. We have two parallel sides. We are given that AX is 4, XB is 10.5, CY is 6, and BY is X that we're trying to find. It's all marked, so we're good to go there. We can just set up a proportion. 10.5 over 4 equals X over 6. Cross multiply. So we have 4x is equal to 10.5 times 6 is 63. We divide by 4. So x is equal to 15.75. And guys, on both of these, it's totally fine to get decimals. I do want to talk about, because up here in our theorem it says it says these are similar by angle-angle similarity. I know it looks kind of like there's only one triangle here, but let's talk about this whole angle-angle similarity thing. So we have these two parallel lines, and we have this transversal. These angles are corresponding angles, making them congruent to each other. If I switch transversals, and I looked at this transversal. Oops, erased it instead. These angles are corresponding angles, so they are congruent. So if you notice, our two triangles, this small one right here, and the larger one right here, we have those two sets of angles congruent, so by angle-angle sim, the triangles are similar. I also want to point out that they both share this angle by reflexive property. So you could find a lot of congruent angles here. All right, let's go on to the next theorem, converse of the triangle proportionality theorem. If a line intersects two sides of a triangle and separates the sides into proportional corresponding segments, then the line is parallel to the third side of the triangle. So this is just the flipped version. Now it's saying if these work out, then we know that we have parallel lines. We're not told the parallels. We have to figure out if they are parallel. So, our example, we're going to determine if these lines are parallel. So I need to start by labeling these things. DH is 18. HE is 36. DG is 1/2 GF. Now, that can be a little bit confusing since we have an expression instead of just numbers. Sometimes this is pretty easy, okay? I'm going to ask myself to compare with the other side, is DH equal to 1/2 of HE? So I'm looking at these two parts here. If that is true, then I know that these are proportional without setting a proportion to cross multiply. So then I would know that my segments are parallel. So I'm going to just plug in this information. DH is 18. We have 1/2. HE is 36. If I do this math, I get 18 equals 18, which checks out. That means if I were to plug in, say, 10 here, DG is 1/2 of 10. This would be 5. I'm just making random numbers up right now. These are proportional to each other. The smaller part is half the size of the other part. So we can go ahead and say that GH, segment GH, is parallel to segment FE because the sides are proportional. In theory, guys, you could draw these triangles out as the big triangle and the small triangle. We've actually done that before, but then you would have to be looking at the full side lengths, which can be more work. Totally fine though. Go ahead and pause me and try this next one. Okay, so we know these things. XY is 15. YZ is 25. WA is 18. AZ is 32. We're trying to determine if these lines are parallel, segments are parallel. So what we want to do is cross multiply. So I'm going to say 32 over 18 equals 25 over 15. Now there's nothing to solve for. So technically you don't have to cross multiply, although that's totally valid. You can cross multiply. You would take 32 times 15. That equals 480. And you equal that, or you hope it equals, 18 times 25, which is 450. You guys notice how those do not equal? That means that those sides are actually not parallel. So we can go ahead and say that segment WX is not parallel to segment AY because the sides are not proportional. Okay? You could also, like I have said before, either reduce these fractions or figure out the decimals and see if they're the same. So this one is about 1.7 repeating, and 25 divided by 15 is about 1.6 repeating. So these are also not the same. So there's multiple ways you can check this. Alright, so we're going to finish up with vocab here, which we're going to use at the start of our next lesson. A midsegment of a triangle is a segment with endpoints that are the midpoints of two sides of the triangle. Every triangle has 3 midsegments. The mid-segments of ABC are segment RP, because it is formed by the midpoints of two sides. Segment PQ, same thing. And segment RQ. A special case of the triangle proportionality theorem is the triangle mid-segment theorem, which we will get to in the next lesson, so we'll leave you on a little bit of a cliffhanger there. If you have not gotten fairly far on the 7374 delta, I would work on that with the rest of your time. Or if you're decently far, you can start working on the 7.4 worksheet, which is another page away. Have a great day.